Hello, hello, hello. Good morning, good afternoon, everybody. Good afternoon, Sydney. Thank you. Sydney wins. Not that it's a competition, but it totally is. Good afternoon. Oh, here we go. Now we're talking. All right. I'm assuming this means you can hear me. Awesome, awesome. So yes, good afternoon, Sydney. Good afternoon, Yaneli. Good afternoon, Kaya. Good afternoon, Roger. Good afternoon, Erica. Good afternoon, Ariana. Good afternoon, Matthew. Thank you for being so early. Sorry to cut you off when I was in the other class. Or I mean to kick you out of the waiting room, blah, blah, blah. Good afternoon. And if that ever happens, guys, if you're in the waiting room and then you get kicked out from it, it's just because I'm transferring from the other class, but I see you. Good afternoon, Genesis. Good afternoon, Samantha. Good afternoon, Brandon. Good afternoon, Gabriella. All right, all right. Um, good to see you all, even though I'm seeing none of you at the moment. Um, okay, we're gonna get rolling today. So the purpose of today is to finally get to, oh, hello, not what I meant to do. Sorry. Okay, the purpose of today is to get to homework 4 to Gabriella, thank you for doing a public service. Awesome. All right. And points, points, points. All right, we're getting to homework 4 to the concept and the problem solving of average acceleration as well as instantaneous velocity. That's like the concepts on the docket now. Now, so it's all about homework 4 today. Let me do a brief, indulge me please in a couple of quick announcements and a brief recap of homework 3. Announcement number 1 is now if you've turned in, I think I was 100% up to date with you guys as of last class, but if you've turned anything in at all, first drafts or redos of anything in the last 5 days, I apologize, I haven't gotten to it yet. So it's not you and it's not personal, and I'm aware of it. But so I owe you points now. I owe you things. The ball's in my court. Bear with me, please, and thank you. That's number 1. Number 2, we're going to homework 4 now. Now, again, this is a slightly jostly experience for some people. There's 2 threads always in physics. There's a conceptual thread and there's a computational thread. And they're constantly weaving in and out of each other. And sometimes it's hard to see the connection between the two. And sometimes it's vital to see the connection between the two. But so, for example, we were doing like homework 2 was kind of computational. And then we did this left turn, and homework 3, the train of thought, Gedanken experiment, which seemed very conceptual. And now all of a sudden we're back to a mathematical looking thing. That can be confusing. I understand. What I want you to, I'm going to recap the concept that we are trying to take away from homework 3. And I'm going to tell you right now that it is a crucial concept for the rest of physics. It is the most fundamental, in my judgment. It's the most fundamental concept that there is in physics. It underlies every problem we ever do, even when we don't immediately see how or why. And sometimes, especially when we don't immediately see how or why. So I'm going to recap the concept, but I want to remind you also, like people tend to think, some people are scared or intimidated by physics, and yes, physics gets hard. But there's I think, a misimpression in the world that what makes physics hard is the math. I don't know that that's actually my experience with students. My experience is that, in fact, you guys are very well equipped with mathematical computational techniques, and that once anybody, and I can't speak for you, but in my past experience, it tends to be the case that when a student is helped a little bit to tell what kind of computational procedure they should do to solve a physics problem, they're often very, very good at it and very comfortable and relaxed at doing computations. The tricky thing for students, and including me, often is, okay, but which computational procedure do I do? Like, what kind of math am I supposed to be doing? How do I set up the math? Like, how do I do this physics problem? How do I start it? Once I see that it's math, I'm okay. But how do I get from the physics to the math? And what I'm here to tell you is, well, the simple answer is step 1, 2, and 3 of the 5-step process are all about, particularly step 3 is all about knowing what concept, which often ends up meaning equation, to use in order to start setting up and then turning the mathematical crank. And what I mean, and of course, we're going to get a lot more equations and definitions like average velocity, or like the one on the sheet right here, average acceleration. We're going to get more and more equations that will be in your arsenal for what you use to do a step 3 GDP. When you're solving a problem that looks mysterious at first. So sure, you're going to get more and more equations and definitions and stuff. But what I'm here to tell you is underneath all of those equations, the granddaddy of all the GDPs, the GDP to turn to when you really don't know what's going on in a problem or what the issue is, the granddaddy of all of them is Galileo's principle of relativity. The thing that we established at the end of last class. I'm not going to write it again now because it's going to confuse these notes, but you may want to turn back in your notes or remind yourself, Galileo's principle of relativity is a principle from which the laws and even many of the definitions of physics emerge. Like it comes before the laws. It's about how the laws work. That's how deep it is, right? I mean, literally, the original form of the principle says the laws of physics, whatever they are, whatever they're going to be, the laws of physics hold the same at all constant velocities. Or put another way, the way we're going to start putting it more and more, or the laws of physics. I mean, that's the way I said it last week. If you're taking notes again, another way you could start putting it now is the laws of physics hold the same in all inertial or unaccelerated reference frames. I'm going to say that again. Another way you could put, and this is still form 1, just slightly different words. Remember, if I change the English, don't try not to be upset. I mean, Galileo wasn't writing in English in the first place. I said last week, the laws of physics are the same at all constant velocities. Another more sophisticated way that I'm going to start saying that now is the laws of physics are the same or hold the same at all inertial reference frames. Now, what does inertial mean? It means unaccelerated. It means not accelerated. It means maintaining the same velocity, the same speed, and the same direction. So what I am, and what is a reference frame? I'm going to get into that in like 1 minute. But what I'm saying is the big takeaway from last week is that however fast you're going, as long as you're going a constant fastness, and whatever direction you're going in, as long as you're going in a straight line, however fast you're going or whatever direction you're going in, the laws of physics are the laws of physics, even the ones that we don't know yet. They're not going to change from one speed or one direction to another. Therefore, so that's form 1. I'm just recapping again. Form 1 of Galileo's principle is the laws are the laws. They don't change from one constant velocity to the next. Therefore, we said form 2 is, well, therefore, if that's true, then you can't do an experiment to find out how fast you're going or in what direction you're going. If by that you mean how fast you're actually going or what direction you're actually going. Like you literally cannot, ever, no matter how advanced the technology is, no matter what laws evolve in the history of physics, it's not possible to do an experiment to find out how, like if I'm in the airplane and it's totally visibly apparent, it's totally possible to find out that like I have motion relative to the clouds or relative to some trees or relative to an airport that I see down below, like, or in train of thought, you can see clearly that there's motion between two objects. But if you're one of those objects and you go, hold on, what I want to know is like, I can see like it's rushing past me or I'm rushing past it, but I can't tell which is which. I want to know, am I the one actually sitting still while stuff goes past me? Or am I the one, or is that stuff sitting still while I go past it? If you want an actual answer to that question, like who in the universe, who in absolute space is actually moving right now or or moving with a velocity of 0, or moving with a velocity of non-zero. And if it's non-zero, what is actually that velocity? If that's what you want to know, what Galileo's saying is, sorry, that you cannot do an experiment to figure that out, because, and that's counterintuitive, by the way. Like, the reason I'm yelling about this is, like, it is fundamental, but it's not obvious. Like, no one thought this for 2,000 years. And what we're saying is, any experiment you would do, like drop something from your hand, like, the idea behind the experiment is that if it resulted one way, it would tell you you're sitting still. And if it resulted a different way, it would tell you that you're not sitting still. That would be the idea of doing an experiment. But what Galileo's saying is, but dudes, if the laws are the same, whether you're sitting still or you're going 100 miles an hour, if the laws are the same, then no matter what you're doing, the experiment's going to result the same. And of course, everybody actually knows this in their minds. Otherwise, they never would get on ships or airplanes or elevators, right? Because you actually assume, we in our bodies actually assume that life works out the same way, whether you're in an elevator or an airplane, or like that you can eat your food, watch a movie, walk to the bathroom, have a game of catch with someone. You can literally have a game of catch with someone in an elevator, and it's like fun, but it's like fun because it totally works. As long as the elevator is cruising, right? Like, not when it's taking off or coming in for landing. That's different. That's acceleration. That's why we have to get to that next. But as long as the elevator or the airplane or the whatever is going at constant velocity, all experiments work out the same. All activities work out the same. Therefore, you can't do an activity or design an experiment to figure out if you're actually moving or not. That's form 2. I'm just recapping. That's form 2 of Galileo's. Why am I calling? I'm saying it's not a different principle. It's the same principle, just said a slightly different way. It's like honing in it, and we're just making a logical inference from the first form of the principle. We're going, okay, if the laws are all the same, which seems pretty, I mean, of course, how could the laws not be the same? I mean, they're laws, so that seems self-evident. So then we're going, oh, but if the laws are the same, then all experiments would work out the same. So I guess you can't do an experiment to actually answer the train of thought question, like, am I moving or not? Like, actually. So then form 3 is, oh, then at least scientifically, at least experimentally, at least physics-y, then there is no actually moving or sitting still. This is the big point, and it is a very big point. We're saying, if from here on in, as physicists, how we arbitrate truth is with respect to data, measurement, reproducible experiment, like, right? Like, it's not just math, and it's not just philosophy, it's physics. So our truth is tethered to what we collect, the data, the information that we collect in reproducible experiments. So if we just said in form 2 that no experiment is ever going to reveal the velocity of one object, the actual absolute velocity of one object, if all you could ever get from an experiment is the velocity of one object relative to another, then form 3 is saying, well, then that's all there is in physics from now on. From now on, and I mean this, I mean, from now on, 1632 up to 2024, like past Einstein, like this is where Einstein like picks up on this idea, is that means, this is form 3, velocity is never a property of a single object anymore. It's literally meaningless in physics to say, how fast is the Earth going? Like, actually. Or to say, what is sitting still in the universe actually? Like, if it's not the Earth, is it the sun? No, the sun's going past the galactic center. Is it the center of our galaxy that's actually sitting still in the universe? No, our galaxy is spinning around the center of the Virgo supercluster, et cetera, et cetera. Like, now what we're saying, and not even that Galileo even knew about those things, but if you take Galileo seriously, we're not just saying, in other words, people used to think the sun and the planets and the stars were revolving around the Earth, and that they thought the Earth was sitting still at the center of the universe. And that is not unreasonable. It's not stupid. And it produced huge amounts of absolutely helpful and informative and accurate data. It's very productive and reasonable to believe that. It's just not right. But it's also not right to think, oh, thanks to Galileo, we now understand the Earth is not sitting still at the center of the universe. The sun is. No, that's not the point either. The sun is not sitting still stationary at the center of the universe. The sun is sitting still at the center of the solar system, which is just the system of stuff that we declare to be going around the sun. That's like saying Dan Yaverbaum is standing at the center of the Dan system. Yes, I am. Like it, the sun is also moving at 650,000 miles an hour past the center of the galaxy. The center of that is moving on and on and on. So what we're saying is, in form 3, there is no objective center. There is no actual velocity of any one given object. What velocity is a comparison. No velocity is a property of a single object through space. All velocities are relations, or every velocity is a relation between two objects. Okay, velocity is relative. It's a comparison. That's form 3. There's going to be other forms. There's going to be more implications of this. In fact, every next topic or chapter we ever do in physics is yet another form of this principle. It's one principle. We just keep turning the conceptual crank as though we're doing substitution, algebra on an equation. We're just like doing that to a concept here. So you're going to keep getting more forms. The form we have so far is 1, 2, 3. I have to say a little bit more about, well, so now again, we're going to soon turn back to the math. Sometimes when you're doing the math, you're going to be like, why do we spend all this time on the concept? I don't see what it has to do. I'm just doing math here. Like, what does that have to do? You'll see more and more. If you ever don't feel like you don't see the connection, that maybe in that moment, the connection's not overwhelmingly important in that moment, maybe, but also just as likely, sometimes you're going to really see these concepts at work when you have to set up your math. You're going to see that in a minute. Even in an easy problem, particularly, I keep saying step 3, but particularly also step 1, diagram and fact pattern. From here on in, well, I'll turn this just so you see, so we're making some progress. Yeah, from here on in, as we start looking at problem 4, homework 4, even the quick reviews at the top, which are quick, and I'm sure most people, I hope, maybe got correct answers very quickly to the quick reviews on top of homework 4, but I'm using them as an example to get some concepts out here. Like from here on in, when you draw a diagram and fact pattern, we've been saying the purpose of a diagram is to establish labels that define the symbols that you'll use in step 4 of the problem. Well, one of the key things to label in step 1 is what we're from here on in going to call a frame of reference, or a reference frame, same thing. Part of our right and our responsibility from now on, when we're setting up a diagram to do a problem, part of what we want to establish, we want to take that moment when we're drawing the diagram to consciously choose what we're going to call a reference frame for the problem. Now, what do I mean by now, even in this case, even in this case, if you don't even, you might have gotten this problem 1 of homework 4, you might have gotten it right without thinking about any of this stuff, and that's fine. And you might even get full credit for it, you probably will get full credit for it. But because I know you're comfortable with the problem, I'm using it as an example of where we have to start thinking about reference frames. What do I mean by a reference frame? A reference frame is the basis for comparison. Well, here's literally the definition. Please write this. Wait, don't write it down yet. So I'll give you the background. What I'm saying is, from here on in, all velocities are relations, comparisons, right? So from here on in, anytime you're going to say the velocity of something or think about the velocity of something, you have to, somewhere in your mind, and ideally on paper, you have to be thinking of another object to which you're comparing the velocity of the first object. Like, we can't, from here on in, if you say, how fast is the Earth moving? Well, relative to me, it's moving 0. But relative to the sun, it's moving 65,000 miles an hour. Both of those answers are totally legitimate. Both of those perspectives are totally legitimate. But it totally will affect my answer and all my calculations if knowing which one I've chosen to be the perspective of the problem. So from here on in, so here's a definition to please write down in your notes. And you could totally, since it's not on the board, if you send me notes, a screenshot of notes that you're writing this down, like, you'll get points. definition of a reference frame. A reference frame or frame of reference, same thing, whichever you like. A reference frame is a coordinate system and perspective maintained by an observer regarded to be at rest, or you could say regarded to be stationary. Let me say that again. A reference frame is a coordinate system and perspective maintained by an observer. This would be even a better way to say it, regarded to have zero velocity. That's probably even a better way to say. It means the same thing, but so what do I mean by that? I mean, and if you want me to say it again, no problem. I'm sorry, direct chat. If you want me to say that again, you can put in direct chat. Of course, you'll get this PDF, or I mean, you can play the video again too. But what I'm saying is, since I'm saying from now on, velocity is about perspective, like what the velocity of Earth is, or what the velocity of an airplane is, depends on what you're comparing it to. So you always have to specify this other object whose velocity you're comparing to. But if you think it through, the other object that you use as a basis of comparison, you're tacitly always will be calling the zero velocity object. So to say that the Earth is moving 65,000 miles an hour past the sun, if we're choosing the sun as our frame of reference, we're doing, so here's my example, maybe to write in your notes. If you're measuring the velocity of the Earth, you might, for example, choose the sun as your reference frame. If you choose the sun as your reference frame, you are saying two things, and you're making a choice. You're allowed to make this choice because you could choose anything that's going constant velocity. But by making that choice, you're saying two things. One, you're saying in this way of looking at the world, the sun has zero velocity. Okay, in this context, in this perspective, I'm choosing a reference frame in which the sun is moving still. Is not moving at all. That's not an objective statement. Other people could do another frame of reference where they see the sun moving past them. But you're saying, in my perspective, the sun is moving still, is sitting still. That's point number one. And then point number two, you're also tacitly saying, okay, I'm building a coordinate system. Like this is really a perspective now. I'm going to take axes that emanate out from the sun. Like the sun will be the origin of my coordinate system, and I'm going to make an x-axis coming out of it, and a y-axis and a z-axis, or whatever. And now, and every measurement I make will be in the coordinate system, fixed to that sun. And the coordinate system is fixed to the sun. So that means now, this is this sort of tricky piece. It now means that coordinate system isn't just a place. The reference frame is not defined, and you may want to write this in your notes. Reference frame is not defined by place. It's not defined by position. It's defined by velocity. So now anything in the universe that has the same velocity as that sun, i.e. anything that looks stationary, that is stationary compared to the sun, anything that's not moving away or close to the sun, is in the sun's reference frame somewhere. It may be at another location. It may be really far away. It may not be touching the sun. But the sun's frame of reference now includes everything in the universe that has the same velocity as the sun. And then anything else that doesn't has a measured velocity compared to that. So from now on in, a reference frame is like the zero velocity frame, the rest frame, the sitting still perspective to which all other objects' velocities are compared. That's the idea behind a reference frame. So I'm going to say it again. A reference frame is not a place. It's not a perspective defined by place. It's a perspective defined by motion. That'll unfold more and more. But so from here on in, when in doubt, if you're trying to do some physics and you're like, I don't even know, think about the first thing you got to do when you draw a diagram is, what is your perspective? What is the coordinate system? What's included in that coordinate system? What object are you focusing on that you're calling stationary, and then measuring other objects relative to that? Okay, So again, sometimes you're not going to see how you're going to have to be conscious of connecting this concept to the physics computations as we proceed throughout. Now, in a minute, we're going to get back then to the concepts of velocity. We already know about average velocity. In today's lesson or today's homework, we're going to get starting to get into instantaneous velocity. That's another type of velocity, but they're both velocities. They're both have this whole relational character that I just described. So any velocity is subject to the concept that I just said. And even instantaneous, I mean, sorry, even well, yeah, I'll leave it at I'll leave it at that. So we're about to go to problem 4, excuse me, to homework 4, to problem 1, the very quick reviews. They are quick reviews. So now that I've spent, so I'm basically saying right here in okay, I'm going to do a quick, just for the sake of the video and stuff, I'm going to do a quick screen share so you see what I'm talking about. Hold on one second. Sorry. I'm going to change the screen share just so we're all on the same page, or if you're looking at this later. Right. So, oh, not that. Okay. This is the sheet we're talking about now. When I put the black screen back on, I'm showing you a diagram that I made for this first problem here. Very quick review. Like and then I'm going to bang through the answers. I think if there's any questions on the answers, definitely ask in any direct chat or whatever. I think probably most of you did fine with the answers. I'm just using it as an example for the concept of frame of reference. So we're going to do this problem right here, number 1. Then we're going to do problem number 2, which starts getting into a new concept, and we won't get to problem 3 today probably, and that's fine. So this is the sheet we're talking about here. Now I'm going to go back. I'm looking at the time. So tell me if it's okay, but I'm going to switch back now to my work. I mean, you could take a screenshot of this if it's helpful or whatever, but I mean, you have the sheet. Okay. Oh, why did not? Oh, I thought. Wait, why did it not? Oh. Oh, that's now I didn't even realize that. So you can toggle off the screen. Okay, anyway, well, hopefully you can see the screen share. I don't know if you're aware, but with the new updates, like I guess you could literally toggle it off and not be aware that it's there. But can you all see the screen? You can see the black screen. Yes, Gabriella or anybody? Can you see? Yeah, okay, thank you. Thank you. All right. So quickly, before I get into the answers of it. Oh, and there's something in the chat. Sorry. Yes, thank you, Andre. Great. Okay. Before I get to the answers, and again, I don't think the answers and I'm not saying you have to write all this to get full credit on the homework. I'm just using this as an opportunity to show you how the concepts are linked to the math. So for the very quick review, I drew a little diagram here. I put Berlin up there. All I'm trying to say in this kind of silly little simple diagram, I'm saying, look, I'm going to look at this from the perspective of Rome, this problem. Rome is at the center of my coordinate system, and all there is north and south. It's one-dimensional coordinate system. So Rome is at the center, and then anything to the north, such as Berlin, I'm calling positive direction here. I'm calling the positive direction, and that's a choice. Right? I mean, I didn't have to do it that way, but I have to make a choice. I have to be clear. That's really what we're ultimately saying is you could do this from the reference frame of Berlin. You can make it 0 and you can make south positive, but you have to do something and then stay consistent with it. That's what it means to choose a reference frame. So I'm focusing my origin, my coordinate system on Rome. I'm saying anything to the north of it is what we're going to call positive. Anything to the south of it, we're going to call negative. And now a subtlety that one might not have thought of until Galileo is that This is the frame of reference of Rome. Okay, this is the coordinate system defined by Rome. This is the perspective of the world that we have if we're in Rome. But I want to make clear before I go on, yeah, that Berlin is in this reference frame as well. This is not Rome as opposed to Berlin. Like Rome is at the 0 position and Berlin is to the north, fine. But they're both in the same frame of reference now. Like Berlin is in the coordinate system of Rome. It's in the frame of reference of Rome, not because of where it is, but because Berlin has the same velocity as Rome. It's what it says on the side here. Right. Well, okay. It says everything stationary relative to Rome is in the Rome reference frame. Or put another way, anything in the world now that is moving at the same velocity as Rome is in the Rome reference frame. So actually that means like any city on Earth, like they might be really far away, but if they're moving the same way as Rome, then in the same speed, in the same direction, then they're in the same reference frame as Rome. And what is that speed and direction? Well, we're calling it 0 because we're choosing to look at it from Rome's point of view. So therefore, if I was in Rome and I had a telescope or whatever, and I'm looking at Berlin, I don't see Berlin moving. Berlin's just sitting there. So even though it's very far away and it's not attached, it's in my reference frame. If I were to look at a car or something even really close to me, or even a mosquito on my desk, if the mosquito's moving past me, then it's in a different frame of reference frame. Even though then it's in a different reference frame, like a mosquito. Even if it's 2 inches from me in my office, if it's moving past me, it's not in my reference frame. Like I can see it, it's in my visual perspective, but it's not in my physics reference frame. As opposed to Peking, which is super far away and I can't even see it and it's not even attached to me. But if it's moving at the same velocity as me, which I'm calling 0, then it's in my reference frame. So a reference frame is a coordinate system defined by velocity, not by position. Like the coordinates might be defined by position, but the coordinate system, the axes, like are defined by velocity. And if it's your reference frame, then the velocity of those axes you're declaring to be 0 and everything else moves past them. Okay, I just want to establish that now. Here are the answers, just to the quick review. Sorry, here are the answers. I'm sure I believe many of you got them right. You could check and just, if you have any issues, you could tell me, but just note, basically, this is just like review. It's having you note that when it's distance or average speed, those are like the scalar quantities. You always get positive answers for those. Like direction has nothing to do with scalar quantities. But when it's asking you about vector quantities such as displacement or average velocity, then negative signs could come into play. Direction does come into play. In this case, the direction is south. We called it negative. So I got negative answers for those. Now, okay. Also note that whenever it's like the vector quantities like displacement or average velocity, then I tend to use symbolic notation. Like it looks more like equations. When it's not talking about direction and it's just saying like scalar quantities, then I tend to just keep it in English. But those are my answers for those. So you can look to see if is there any confusion or could you just raise your electronic hand if you're probably bored, but as long as you're clear with where I am so far. Could you just, cool, thank you, Sanam. Thank you, Kaya. Thank you, Sydney. Thank you, Yaneli. Thank you, Samantha. Thank you, Erica. Thank you, Genesis. Thank you, Ariana. Awesome. Oh, and 10 other, wow. Awesome. Thank you, Skylar. Thank you, Matthew. Thank you, Andre. Thank you, Gabriella. Thank you, Brandon. Okay, so I'm assuming that's clear. So if that's clear, and if it's not clear, put something in the chat. If that's clear, I'm going to pause for a second. Obviously, we want to get into the sort of the harder thing, but we're going to pause for a second. I'm going to actually pause the recording. Okay, recording back. Oh, sorry. And the other people who are if your hands are still up from saying you get it, thank you. You can put them down. But if you have a question, feel free. So like Brian, thank you very much. If you have a question, go for it. Or if you're or you can put your hand back down, Brian, or eat. Well, okay. I mean, Brian, you good? Or okay, thank you. Awesome. All right. So now back to homework 4. So now we get to the next question, instantaneous velocity. Now here comes another example of a question where in the end of the day, the answer is not that hard. I mean, to actually do the math of the answer is simple once you see it or once you get it. But this can look at first like a very unfair or weird physics question. Like this is an example where I'm all of a sudden asking you about something that we don't have a formula for. That's on purpose. If you look like, and I seem to be asking you something very, very specific. Like I'm saying all these facts about a car and 30 minutes and 40 miles, and then I'm asking like how fast is it going at the 18th minute, 42nd second? Like, so what? I mean, but I never gave you a formula for how to do that. And by the way, if you even realize that, if you even realized, wait, we don't actually explicitly know how to do this, that's actually a good thing, because that means you're at least recognizing the first point, which is you do know how to do average velocity. You do have an equation, a definition. It's one of the few things you have. You do have a definition for average velocity. But if you recognize that that is not what this is asking, good for you, because although they might be related in this case, you're right. It's not what it's asking. So it's asking this question. It's asking, what is the instantaneous velocity at precisely the 18th minute, 42nd second of some journey that it described? So what it's asking is exactly what that word sounds like, and the only thing that we know right now, which is that word. It's asking for velocity at an instant, not velocity between 2 points in time, but velocity at a point in time. That's a new concept. That's what this question's asking. And again, so please understand, this is how physics works. Like we get an old concept, we work with it, and then we're pushed to a new concept. And the idea is that we figure out the new concept from the old concept, not that we get a match. And it's all ideas. Basically, I guess what I'm trying to get everybody used to with the nature of these homeworks and stuff is that to do physics like a physicist is not to redo physics. It's not to recite physics. It's not to plug in physics as you might have expected. It's to invent physics. To do physics is to pave the road as you go. And why that's okay, and it seems and it feels unfair at times. It does. But why it's okay and fair for us to make physics as we go is because the belief of physics, the assumption, the attitude of physics is that it actually makes sense, that it's a bunch of logical inferences that flow out of truths that we find self-evident. In other words, the reason that Newton or Galileo or anybody could make this stuff up is just because they spent the time on it and they cared. It's not that they had access to some magic box of formulas that you don't have access to. It's they were thinking logically about the stuff they already knew. And that's what we have to do to be physicists. So in this case, we're suddenly being asked, how can I know, can I measure or predict how fast a car is going at a moment in time? How would I possibly do that if all I already know how to do is figure out how fast a car is going during an interval between 2 points in time? So I'm not being asked average velocity. I'm being asked somehow to use my understanding of average velocity to get to a concept of instantaneous velocity. Well, so if I were solving this problem, I forgot to write down step 1 and step 2. Forgive me. I think you could figure them out at this point. But like, if I were solving this problem, I would go to step 3 GDP. Like, I would write down something that I know is true, that's true even before the problem starts, that's like a definition or a principle, and see if I could get from there to what I'm trying to figure out. I won't be done at step 3, but I'll write down step 3. So I write down the one thing I know, that average velocity is displacement per time. So now I'm starting to think, can I get instantaneous velocity for that? Well, if I like start plugging in, if I'm like, all right, average velocity is how far you get per how much time you take. Here, we're asking to look at like rate, this kind of rate of velocity when the interval of time is 0, right? We're not looking between 2 points. We're looking at a point. So we're looking at the interval of time during like from like 4 o'clock to 4 o'clock, not 4 o'clock to 4:01, 4 o'clock. So presumably we would plug in 0 in for the time interval if we were just plugging straight into the only definition of velocity we have so far. But then if we plug in 0 into the denominator, that's weird because first of all, you know from math class that anything divided by 0 is like a blow up. It's like infinity or undefined or something. But then worse than that. So what I'm about to say is if we just take our straight up definition of average velocity, if we don't adapt it somehow, and we just assume that it carries over to individual instants, something is going to go wrong. And if you're taking notes, separate notes, I'll tell you 4 things are going to go wrong. Like if we just plug straight into average velocity to get instantaneous velocity, it's going to blow up on us in 4 ways. Here are the ways that it's bad to do that. Number 1, we're going to get 0 in the denominator, and that's always confusing in math. Number 2, if you look at a point in time, if you're asking how fast is a car going right now, right? Not over the movie, but at the frame, like in the snapshot. How fast is the car going right now? Well, you ask, well, how much time has elapsed? None. So you put a 0 in the denominator, and then you go, well, okay, so how far did it get? In none time, how far did the car get? None place, right? Like a car doesn't move in no time. Well, I mean, I don't think it advances anywhere in no time. If it's 4 o'clock, the car is here. In a snapshot, it's a freeze frame. The car seems frozen. So now you're going to put 0 in the numerator. If you're just plugging straight, if it's just math and not a concept, you're going to plug 0 into the numerator. So now that's a new problem because 0 over anything is 0. So if you just look at that numerator, you're going to get no motion at all. But if there's no motion in every single frame of a movie, then how is there a movie? Like the car had to move somewhere, somehow. And if you're going to say that if I'm going to say that at every instant, there's 0 time and therefore 0 displacement, so there's 0 speed, then you just have a bunch of frames that all have nothing speed in them, so they can't add up to motion. So that's problem 2. So problem 1 is 0 in the denominator. Problem 2 is 0 in the numerator. Problem 3 is anything over anything is 1, right? I mean, 7 divided by 7 is 1. 4 divided by 4 is 1. X divided by X is 1. 0 divided by 0 looks like 1 to me. So now, by that reasoning, if we just plug in, if we just are trying to adapt average velocity directly to an instant, and we're not careful about it, we got so far 3 problems on our hand. 1 is it looks like infinity all the time or undefined all the time. 2 is it looks like 0 all the time. 3 is it looks like 1 all the time. And the 4th problem is that whichever one of those you choose, if one of them somehow makes more sense to you than the other, Quark bless America, but whichever one you choose, you're now saying that's true all the time. So right, because it's either always 1 or it's always 0 or it's always undefined. So that means that the motion of any object ever at any instant is the same as every other instant and every other object. That can't be right. When you're pulled over by a police car, when I'm pulled over, I mean, it never happens, of course. But if I were pulled over by a police officer and they're like, sir, do you know how fast you were going past that school zone, that sign that said school zone, that said children crossing 20 miles an hour maximum? Do you know how fast you were going when you went past that sign? I can't say to the police officer, well, I'm a physics professor. Let me explain to you. I've been in the car for like 2 hours. And I only traveled in those 2 hours. I mean, I have a stopwatch with me and I have a ruler, and I've been traveling for 2 hours and I only traveled 3 miles in those 2 hours. Now, granted, I was at a rest stop using the bathroom for like an hour and a half of it. And then I was in the right lane going backwards for another hour, blah, 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 blah. But on average, sir, like if you do displacement per time, I did 3 miles or whatever I just said. I did 1 mile in 3 hours. So on average, I'm going 1/3 of a mile per hour. So I don't see the problem, officer. That's ridiculous. I hope you understand. I don't care if I'm a physics professor. Like that would be the stupidest possible thing I could say to a police officer. Even if it was right, it'd be a stupid thing to say. But because that's not what the police officer's asking. All of what I just said might be totally true, that because I sat at a rest stop for hours, it averaged out to like less than a mile an hour for the average for the whole thing. That's not what the police officer's asking. They're like, dude, when you, when you went past the sign, in fact, if that's true, dude, if your average was 1/3 a mile an hour after you spent all that time at a rest stop, then that means for that average to be true, you have to be going super fast at the moment I'm asking you about. I'm asking how fast you were going at that point when you passed the school zone sign. I'm not asking average. I'm asking instant, and don't tell me your instant was 0/0, or don't tell me your instant was L'Hopital's rule or something. You instantly were going very fast. I got it on my radar, like, and it matters because there could have been a child there or whatever. I'm not only gross, but right. So there's clearly a meaning to how fast something's going at a moment, and it can't, or at an instant, and whatever how fast something's going at an instant can't be the same answer as how fast everything else is going at an instant. There's got to be a number that we can get for how fast, but we can't get it by just plugging directly into the average velocity. So we've got to do something better. This is where, again, concepts then lead to equations, but don't just jump from one equation to another. What's the concept here? The concept is, if it goes back to a movie of motion is what we do understand. A movie of motion, an interval between 2 points in space and time is the first thing that we can visualize, measure, and compute. That's why we start the course and all physics with average velocity. That we can get our mind around. But it's not precise. It's visualizable and measurable, but it's not precise. So we start with average velocity, and then the idea is we're going to, because we know if something's happening in this whole movie, then somehow we should be able to zoom in from the context of the movie and see what's happening at any individual frame. Somehow we've got to be able to use context to zoom in to the individual frames and realize what's happening there. If we just plug into the individual frames, no, not going to work. We've got to zoom in from the context. And if you want to think a bit more mathematically, if this is a graph, if we're thinking a graph, and on this axis is time, and on this axis is position, right? We look at the whole graph. If we look at the whole graph, what average, and please write this down in your notes, I don't have it in these notes here. If we were to make a position time graph, xt graph of motion, if you think about it, no matter how complicated the curve is, no matter how complicated the motion is, if you pick any 2 points on the graph, on the xt, the position time graph, if you pick any 2 points on the graph and imagine a dotted line, straight line going between the 2 points, I will write that. I think this is worth putting in your notes. Hold on. I'm gonna add a page here. The other section, well, they don't get this page. Hang on. How do I do it again? Hold on. I'm gonna add a page. Okay. Ah. Just to be clear, if you make, and I'm not saying you had to do this for this problem, again, I'm using it as an opportunity to explain things. If you make a graph of any kind of motion where the independent variable is time and the dependent variable is position, which is like the only things that we're dealing with so far, no matter how complicated the motion is, if you take the slope of the straight line between any 2 points, in other words, even if the graph itself is like not a straight line, but if you imagine the straight line connecting any 2 points on that graph, the slope of that line, the rise over the run, like delta y, like y2 minus y1 over x2 minus x1. Well, on that graph, it's not y and x, it's x and t. So the rise would be x2 minus x1, and the run would be t2 minus t1. The rise over the run, the steepness of that straight line, the slope, right, is, if you think about it, what we're calling in physics average velocity. The average, I'm literally saying, well, it said the average velocity of some motion is the slope of the straight line connecting 2 points on a position time graph, right? That's a way to graphically visualize. In other words, that's the straightforward thing. Even if the motion is complicated, you could take this average, the average rate at which the graph advances, the average rate at which the object advances in space per time. Slope on position time graph between 2 points equals average velocity for the average velocity for that motion depicted by the graph. Okay, right? So I'm saying that, so average is like, we can picture it and get it even on a graph, but notice the whole thing is that's just the average. That would be the rate of the yellow dotted line, but the thing didn't actually move along the yellow dotted line. So what we're really interested in is the slope at any given point in the blue line. Now it's going to be, so if we're interested in like the slope, oops, if we want v without a bar on it, if we want instantaneous velocity, like no bar, we want the slope at some point. How are we going to get that? Well, it's going to be somewhat, if we pick 2 points around it, the slope between those 2 points is sort of close to the slope at some intervening point, but it's not exactly the same, right? And you've heard this before. I'm sure this is familiar. You could see what I'm saying. Like, if we want the slope at a point, we're going to zoom in. We're going to pick smaller and smaller intervals, get slopes of smaller and smaller intervals until we zoom in on that point. We can't literally get literally at that point because a point doesn't have a slope. I mean, slope means how far did you get to another point? But what we're looking for is the slope at a point, and the way we get it ultimately, whenever associations are going through your mind right now, the larger point I'm trying to make is the way we get slope at a point, or the way we get rate at a point amidst a larger trend of points, is we zoom in from the larger context and the larger trend. Now, is this soon going to be calculus? Yes, it is, if you're seeing that. But I want to urge you, like always, calculus is not just wizardry. It's not just like some weird stuff that we made up and then like works. And calculus is an elaborate, precise way of thinking of something that actually does make sense. Calculus is a way of zooming in, acknowledging a larger context and zooming into a small slice of that context. So for example, so this is like the precursor, like this is the concept that's going on. But for example, in this problem that we're doing right here, in this problem, I'll even write, I'm going to add another page. Oh, can this work? Can you? No, can't do that. Sorry. I wish you could add a page easily. Well, yeah, I'll just write at the top. If you're thinking I'm starting to move us towards calculus way of thinking, you're right, but please don't like run away. or think, oh, now I'm screwed because I don't remember all calculus. I'm trying to rebuild calculus with you. So yes, I'm introducing graphs, but now I'm saying, look, in this first problem that you're giving here, which by the way, many of you may have gotten right, even for the right reasons, even without thinking about calculus or thinking that you were thinking calculus, or some of you might have gotten right for the wrong reasons. You'll see in a second. But I'm saying if you're going to think of graphs now in this problem that I just gave you, in effect, the graph they're giving you is a horizontal line, right? They're saying, sorry, no, not a horizontal. I'm sorry, not a horizontal, a diagonal line. They're saying you've got this car that's always going the same speed, right? For every moment that advances in time, it goes the same amount of distance, or every minute of time, it goes the same distance, right? So if you're thinking of if you're thinking of slopes and stuff, here in this situation, we've got a graph that is constant slope. So this isn't so bad as it might be. What we're saying here, so we started off. Yeah, I guess I skipped a page. I'm sorry. Okay. So if we go back to this problem now, again, we look at it, and maybe if we're smarter, we're on page, we look at the problem and like, wait, I know how to do average velocity. This problem's not asking for average velocity. It's asking for this new weird thing that I don't know what it is called instantaneous velocity. Okay, what do I do? So what you do is you do a step 3 where you write down what you do know already. You know how to do average velocity. So I write the definition of average velocity, V bar equals x minus x naught over t, right? By definition. That's not the answer. It's not what it's looking for, but it's what I know, and I know it's true before the problem started. Average velocity is displacement over time. So then I start going to a step 4 and I start plugging in. The displacement's 40 miles. The time is a half hour. Those are the units that we're working in, miles and hours. So the average velocity is 80 miles per hour, right? The average velocity, according to this problem, is 80 miles an hour. Now, some of you might have then like circled that and said, that's my answer. I'm done. I would say that's not true. It might turn out to be numerically the same as your answer, but that's not the answer because that's not what the problem's asking for. And like when you do a step 5 final answer circle, if you're really referring back to the original question, as you should, you'll see the question was not what's the average velocity. The question is what's the instantaneous velocity. So I've written down the average velocity. What can I do now? Well, I look at any other information that was given in the problem, any other facts that maybe I wrote in step 1. Another fact I was told is that the velocity is constant. If I'm thinking in terms of graphs, I just said that means it's a diagonal line. If I'm thinking in terms of symbolic notation, the way I would write that and the way I'll write that from now on in physics is if I'm told the velocity is constant, I'm going to write v naught equals v, or you could say v equals v naught. That just looks like gobbledygook, but what's it saying? It's saying, remember, v naught means initial velocity. V naught is initial velocity. Initial is an example of instantaneous velocity. It's the velocity at a special instant, the initial instant. It's velocity at time equals 0. So see, even before we were doing formulas, right, we already had some kind of belief in instantaneous velocity. V naught, what is V naught? I don't know, but I know that whatever it is, it never changes, right? I'm told the velocity is constant. So the way I write that in symbolic notation is whatever V naught was is always what V always will be. The velocity at any instant is what the velocity was at the beginning. I'm over talking this, but so if you ever see from now on V naught equals V, it means the velocity is constant. And that's a fact that is crucial to this problem. It's so crucial that from now on, you could use it as a GDP in the future. Like you can say, the thing in white up here, when V naught equals V, when the velocity is constant, then the average, then the velocity is never changing. So as long as the velocity is never changing, then whatever the average was is what the velocity always is, right? I'm saying, like, if you know that you took 3 tests in this class and you know your average, like if you took 3 tests in this class and I just say, what'd you get on the second test? I don't know. You don't know. I don't know. If I didn't give you any other information, what'd you get on the second test? I don't know. But if I say, I'll tell you this, your average in the class is a 95 and you always got the same grade on every single test. If I tell you those 2 facts, if I tell you your average is a 95 and you got the same grade on every test, then you know on the second test you got a 95, right? I mean, like, duh, right? But that's all we're saying here, but it's important. It's a way of saying, wait, if I know the larger context and I know the average about the larger, if I know the shape of the larger context and I know the average, if I know this darn thing, if I know that the graph has a constant slope and I know what the slope is, then I know the slope at every point. It's not, right? So now it's not true in every problem. If it wasn't a straight line graph, if it wasn't a simple problem, it wouldn't be that easy. But it's a demonstration of you zoom in from context to the inside. So we're saying from now on, if V naught equals V, then V naught equals V bar. Like they're all the same. Therefore, we're saying in this problem, okay, in this problem, V does equal V bar. Now, again, let's pause. This is conceptual. Now, if you just do equations, you won't see all of this. If you blindly try to plug into equations. But if you see how the equations and the symbols work, including equal signs, we're saying, listen, V does not triple. So I'm at the bottom in the yellow on this sheet. I'm saying in general, I'm saying this. V does not get defined to be V bar. They have two different definitions. They're two different concepts. But sometimes they can have the same numerical value. By discovery, under particular conditions, we could say that the average velocity and the instantaneous velocity are the same. Just like your individual test score is not the same as your average, but they can be the same in certain cases. So if you're always getting the same velocity, then your average velocity is your instantaneous velocity. Therefore, in this case, therefore, here in this problem, at the 18th minute, 42nd second, as intimidating as that might have sounded to some of you, and to some of you, this is all boring and you saw all this already, and I apologize. But as arbitrary as it sounded, or whatever it sounded, 18th minute, 42nd second, I'm saying the velocity at that moment, the V with no bar on it, is 80 miles an hour because the velocity on average was 80 miles an hour, and apparently the velocity never changed in this case. So the answer is 80 miles an hour. Now, that's the answer, right? That's the answer to problem two. Okay, as usual, I'm over explaining something that to some of you people were sort of obvious, maybe, but there's two big takeaways here. And again, my point is better to over understand this stuff when you think you understand it than to try to over understand it when you don't understand it, if you know what I mean. Like, build a life raft on land. Don't build it in the middle of the ocean. So the two takeaways from all of this rant is, number one, just because a question like starts introducing a new concept that you don't yet have a formula for, that does not mean it's not doable. We're not here to refer back to old formulas. We're here to develop new equations. Okay, we don't use equations. We make equations in physics. That's number one. So in a minute, I will turn this into an equation that we can use from now on. But number two, notice, even if I did more about this than you did when you did it, and even if you got the right answer, I will alert you. Say, like, because I haven't graded this homework yet, I don't think. And if this were an exam or something, if you literally just wrote on the piece of paper, V equals like 40 divided by 0.5, 80, done, answer, that'd be wrong. Like, that is, even though the answer looks right. This is the advantage of the step method is you get points even when you don't know what you're doing, and it helps you do what you're doing even if you don't know what you're doing. But the disadvantage of the point method, of the step method, is like you don't get full credit just for an answer if it's not for the right reason. So if you literally just wrote V equals 40 divided by 0.5, 80, that's my answer. I'm saying, whoa, you skipped something major. Like, that's the average velocity. That's not what the question's asking. You have to show me some kind of reason how you got from average velocity to instantaneous velocity. Now, how did I get that conceptually? This is, I think, the second to last page of the notes, I think. Like, so I'm saying from here on, of course, from here on in, problems could be harder. The graph could be curved, or, yeah, I mean, it's not necessarily, we don't have always this advantage that that the slope is, we're in the general, when we're trying to get instantaneous velocity, we're trying to get slope at a point. My big lesson is, will we always get slope at a point by somehow zooming in from the context of the whole graph? Yes. Will the whole graph always be constant and be this straightforward? No. So how do we do that in general? Well, that's the whole point of calculus. right? I mean, I'm sure many of you saw where I was going a minute ago with that. If you want to get slope at a point, your of a graph, your measurement of that slope gets better and better, more and more accurate as you pick a smaller and smaller interval surrounding it. What we want to do to get instantaneous velocities, we want to get average velocity between 2 points, but in the limit, in the limit as the 2 points get arbitrarily close to each other. We want to know the slope of the straight line connecting 2 points on a position time graph in the limit as the 2 points get arbitrarily close to each other. Why do I and the way to do that graphically is slope of the tangent line at that point. Why am I saying limit? Like, what is limit? Because I'm saying the farther apart those 2 points are, the less accurate. Like, if you want to know the velocity right now at the 3rd minute, you could take the average from the 0th minute to the 50th hour, like my stupid example with the police car pulling me over. If he wants to know how fast I was going right then, or she wants to know how fast I was going right then, and I start talking about what I've done in average for the last 4 hours, like, that's absurd. There could be so much variation in those last 4 hours that it will be related to what I did a minute ago, but it's not going to tell you the number. But if I want to get closer and closer to the actual number, we would take an average over an interval that's smaller and smaller and try to squeeze down. Like, if I'm like, well, in the last 2 minutes, I know I only covered like, now we're talking about something, right? So you want to get as close as you possibly can to that moment. You want the 2 points to be as close as they can to each other, almost to be right on top of each other and be 0, be literally 1 point. But you can't go that far, because if it's 1 point, then it's 0 over 0, nothing happened. So what we're talking about is getting as close as you can, the 2 points being as close as they can to each other without actually being on top of each other. And that's called a limit. And if you think that's like a weird non-mathy idea that you've always hated, well, first of all, join the club. It doesn't seem mathy or precise at all. But in science, it's 1:30. In science, it just means get the 2 points together so close in time that they're too close to be measured, but far enough to be not 1 point. An interval of time that is clearly some time, but not big enough to quantify differently from any other interval of time. Smaller than our measurement threshold. That's what limit means in science. Smaller than our measurement threshold. It's very concrete. So in the end, I know it's 1:30. In the end, now I'm not saying you're going to compute with this. I'm just linking the concepts together. From now on, the definition of instantaneous velocity is average velocity in the limit as t goes to 0. In other words, instantaneous velocity from now on is the derivative, the first derivative of position with respect to time, dx dt. It's like, sorry, I know it's 1:30. It's delta x over delta t in the limit as delta t goes to 0. It's just the limiting case of average velocity. Does that tell you how to compute it? No, you need to know how to take a derivative from calculus to know how to compute it, but that tells you where to look. Okay, so that's 1:30. Thank you for being very, very patient. Goodbye, goodbye. I'll hang out for a second if there's any questions or whatever, but thank you. And the recording is off. Have a great, see you next week. Yes, have a nice day. Thank you.